talking here in this community. So it's, I'm usually in the mid-infrared community, mid-infrared microscopy, and that's what I'm going to talk about: the physics and chemistry of data modeling in infrared microspectroscopy. It was recently at a conference where I was talking in a session. It's called a potpourri of AI methods. So the French, they know what potpourri means. It's a rotten mix of physics, chemometrics, and machine learning. So I'm going to give a short introduction into infrared microscopy. Most people probably are not so familiar with this, and we'll say a few words about model-based pre-processing, which is Harald's baby. So Harald started with this, and I'm not going to show any equations, or at least only equations you can't see from the back about me theory, but just to show you a bit with what kind of interesting phenomena we are dealing with in infrared microscopy. And then I'm talking about inverse scatter problems. So I wrote this POSH for spectral pre-processing. Also, want to shortly mention, I'm leading a group called BioSpec Norway. So we are normally working on a lot of different vibration spectroscopic techniques, Raman and IR on different scales, mainly on fungi, filamentous fungi. I'm going to show some examples on this, and doing a lot of fermentation studies, so using low value materials and producing high value materials in different scales, like from micro scale to big fermenters. And we have a very interdisciplinary group with people from many different domains. So I spent a lot of time during the last 20 years to understand this microscope. So that's an infrared microscope, which was invented in the 90s, and it combines Fourier transform infrared spectroscopy with microscopy. Today it's also available as a system which is combined with a laser, with a tunable, different tunable lasers working in different regions. And so you have, I need to use my finger to point. So you have the sample here, which is typically a microscopic sample, and cells at the size of some micrometers or tissues. And we have optics, which is called Schwarzschild optics. And so we spent a lot of time in understanding this, and also using this understanding and physical models in the modeling of the spectra we are doing. So in infrared microscopy, I also want to show an example. You already saw some examples of this. So we have here a visual image of a filamentous fungus with filaments and also circle-like cells. And then typically in such an when we get the data, we have a full spectrum in every pixel, and state-of-the-art instruments, they have 128 times 128 elements with a full spectrum in each pixel. So a biological cell is a highly scattering and absorbing sample in the infrared, and typically what we get is spectra like this. So if you're used to infrared, mid-infrared spectroscopy, doesn't really look like what you expect, like a nice infrared spectrum. So this is because the cell is at the order of microns, and when you have a radiation with wavelengths at the same order than the size of the object, you get a lot of scattering, and the scattering varies, depends on absorption properties of the sample, it depends on morphological properties, on optical properties. And what happens is that depending on the wavelength,
you may use radiation and very, very interesting effects, which we try to understand in the last years and using them in the modeling. Show you some examples. So PMMA sphere, what you would like to have is something like this, and it's often used as a model system for studying. What you get could be something like this, depending on the size of the sphere. It's an example for a pollen grain. That's what is close to the pure, what is often called pure absorbance. That's what you measure. And also in human tissue, when you have cells, you get this type of scattering. So the scattering of an electromagnetic plane wave by a homogeneous sphere was analytically described already at the beginning of the last century by Gustav Mie. And so this means it's Harald doesn't like this, but there's an exact theory which gives us exactly for this problem all the solutions. So no matter how big the sphere is and how which wavelengths I consider. So what I have got here is what is the theoretical quantity, which you can think of being very similar to the absorbance, and this as a function of what is also often used, size parameter x, or size parameter x, which is in principle the ratio of the size and the wavelength. So you see in the range where these two quantities are approximately the same, a lot of strange things happen. It's called the resonance region, and then you have the Rayleigh region where this is small. It means that the size is smaller than the wavelength, and then the opposite here, the optical region. So we are in this region. So if you, for example, look at such a PMMA sphere and calculate the absorbance, so from this extinction, what is called Q extinction efficiency, we can calculate the absorbance. Then you see, depending on the size of the sphere, here shown for a PMMA sphere, so it has a defined real part of a refractive index, you get very, very interesting extinction efficiency. You also see how it depends actually, for example, on absorption bands, how it changes. So it's a very complex interplay. So how to retrieve the pure absorbance spectrum? So we started out like now more than 15 years ago on building a model which was built on MSc. So you, I guess all of you have heard about MSc and EMSc. It was invented by Harald, who met at the time Jean-Luc Hillary, who was as a postdoc studying together with Thomas in Oss. And it is all of the beginning actually been used by NIR spectroscopy, and in the paper it shows that with MSc parameters you can estimate the size of particles in powders. So it uses actually, it retrieves from the spectrum physical properties. So then I don't need to go into details here, but I just want to remind you, MSc is very simple, but it's a model that works extremely well in infrared spectroscopy, and that's exactly because it uses a reference spectrum, which can order. You can use the average spectrum of the data set, and then you model around this reference spectrum. And let's say normally, if you don't deal with these complicated spectrum as in infrared microscopy, that's a very stable start, because in infrared spectroscopy, like this almost pure absorbance spectra, if you change chemistry a little bit of biological systems, they all look more or less the same. So it gives you a very stable model. So we use this and extended this with models from physics. So we have been working, for example, in modeling with models from physics, these fringes, and then made models to remove them from the spectra, or like for cells, where you have this so-called Mie scattering, we build up models to correct this. And I will go on with the Mie scattering, not further into the fringes. So here the first model, which I put together in 2008. So I mean, first of all, the Mie theory is a very interesting theory, and I spent a lot of time in trying to understand details of it. It's based on Maxwell's equations. You have to solve Maxwell's equations if you are interested in this, and it's you can say it's much more interesting than quantum physics. Quantum physics is based on scalar fields in electrodynamics and electromagnetics. You work with vector fields, so it's quite complicated, but it also has a very interesting and rich structure. So we use this Mie theory, but then we use the so very shortly we start out with an estimate for so-called pure absorbance spectrum. So what we assume is the chemical properties of the sample, and then put this into Mie theory, calculate a scattered spectrum using an assumption for the refractive index and the size of the sphere, etc. And then we do this many times for a large range of sizes and refractive indices, etc. So we take this space of possible solutions, and we actually compress it in a PCA model. So then we use this PCA model, put it into an EMSC, make it fit, and then we get at the end we estimate from this how well it fits with the scattered model, with the measured spectrum. We calculate the error, so then use the error and update the original guess of the pure absorbance spectrum. Then we start the whole thing once more. So it's an iterative process. It's exactly what is described here. And this works very well. So this was actually the final version of the algorithm, which we already published in a paper in this paper in 2010, and we made further extensions on this, and we also used, as Christian explained in the morning, we also use then this Mie MSC in order to correct a larger data set and then train a neural network to correct spectra. So that's now used by quite frequently by this community doing infrared spectroscopy in the medical mainly, using infrared microspectroscopy, for example, for estimating differences between diseased and healthy tissue, cancer versus non-cancer, etc. So then we thought, why not using this interesting and rich scatter information, and probably making more out of this. So biological cells are resonators. We'll tell you in a moment what this means. So when you look closer at this Mie theory, we will see that there are basically two types of features you can see in the spectrum from the Mie theory. So they are related. So one is related to these broader wiggles. These broader wiggles, they're kind of interference effects, like in a film. But then you also have these very sharp ripples. They're called ripples and wiggles, according to a book from Van der Hulst, which was published about the Mie theory in the 60s. So these sharp ripples, and they actually correspond to so-called whispering gallery mode. So that's a mode like this one here, where you get a standing wave in the cell. And that's nicely shown here for different pollen spectra. How well actually you can see this ripple kind of structure, and you have very many of them. You can have them in two, like one here and then one in the inside. They can have, also depending on the number of nodes you get. So each time when you have a frequency, or a wavelength, which is such that you can fit these such whispering gallery mode inside with a certain number of nodes, you get such a ripple here. What does it mean? The whole thing lightens up, and then you lose light in all directions, and this light will not reach the detector at the end. So it looks like an absorption peak, but it's not. It's actually purely to scattering. So then we thought, okay, why not think if you can use this for estimating optical properties, and went back in the literature and find interesting formula for using distances, for example, between these ripples in order to estimate the refractive index. So this is just to show that actually you can from the spectra derive immediately optical properties of the sample simply by looking at the distances of these ripples. So to draw conclusions from frequency spectra about the shape of a resonator is an inverse problem, and this is something which has actually been discussed since quite a while. But from the beginning, I mean, from more or less the beginning, people also wondered, does a frequency spectrum define uniquely the shape of a resonator? So meaning that if you have a mesh spectrum, can you know everything about your sample? So there was a paper in the 60s developed by Mark Kutch in the 60s, and he asked actually the question: can one hear the shape of a drum? So it's a bit different problem, but in principle it's the same thing. You have a drum where you have a what is it called? The thing in the drum, the
membrane.
Huh?
The membrane.
The membrane, yes. You have a membrane, and then from the frequency spectrum of this membrane, can you say something about the shape of the drum? And actually, it was shown then actually before people could make like really great calculations and so on in the 90s by showing an example where there were two shapes of a drum, which gave you exactly the same frequency spectrum. So it's an ill-posed problem. And that's the same for this extinction efficiency. So you can look at the absorbance as a function of the refractive index for one defined frequency, and you see that actually you get the same values for this. So that's for a sphere where you don't assume any absorption. We just look at this at the scattering, and you see nicely this that we have several extinction values which refer to different refractive indices. So then we have thought, okay, it's what we need to do is to condition the problem, and we can't solve this for everything, like for every particle. So you need to condition your problem in order to be able to go back and study deformation of spheres, and we studied nested spheres, and also the dynamics of the ripples and wiggles, and we've published a lot of papers about these. You can say the physics of these systems, and also how the spheres behave in a context. I mean, a cell in a tissue, that's a sphere in context. It's also interesting how this looks like and how this extinction efficiency, how it changes. So then we like everybody, when deep convolutional networks, neural networks came up, so we were also working with these, and I will show you how we addressed the problem. So we had we said, okay, let's condition the system in a way where we have a two-layered sphere. So we have the inside of a cell, we have the cell wall, and then we assume a certain chemistry for the cell wall. We assume a certain chemistry for the cell interior, and we generate, using Maxwell's equations, the measured spectrum. Also, we simulate a measured spectrum. So then we have to do this many times. So we did this, you see, we used chemical training data. So we had around 2,000 pure absorbing spectra from 12 data sets covering fungi, algae, bacteria, new components, etc. For each of these data set, we used principal components of a PCA model with many components, and we sampled from this distribution in order to obtain the absorption properties. From these absorption properties, then we added from a distribution of refractive indexes, like real part of the refractive index and constant part for the inside and for the outside. And then we calculated the so-called fluctuating part of the real part of the refractive index. We put everything in mean theory. And we did this for really big simulations. So in principle, we had quasi continuous sampling with a measuring precision. So you can think of simulating 10 to the 13th spectra, something like this. And we got a very big data set. And we trained a deep convolutional neural network, which then was able, we hope that it's able to, from the measured spectrum, to predict the cellular spectrum, the cellular spectrum, but also we used the so-called shape map, where we also got the distribution of the real part of the refractive index. So this gives us the size of the cell and also the size of the cell wall. So and then we validated this by different systems, cell systems we had. And the first example is here. So that's a filamentous cell, filamentous fungi cell. See liquid bodies inside. So that's one of our systems we work on, because we are interested in producing lipids using filamentous fungi. So we were able then from the spectrum, the measured spectrum here, to predict with this deep convolutional neural network the inside spectrum and the cell wall spectrum, which then afterwards turned out to be very well fitting to when we extracted the cell wall and got like a macroscopic spectrum of them, or when we used what we knew is in the inside as lipids. So worked very well. We could also check with pollen and algal cell. So here you have the predicted spectra inside and outside, and here's the distribution of the real part of the refractive index. So for example, for the pollen, you could nicely see that actually the cell wall spectrum contains sporopollenin. So that's exactly what we expect from the cell wall, and also the sizes and so on. So from this paper, we could show nicely that we got the approximately the sizes which we expected. I say approximate because it's very hard to measure the size of a pollen exactly under an infrared microscope, but we did some tests on this, and this worked out very well. So conditioning, the inverse scatter problem. When I talk about conditioning, what do I mean here? So we have for this ME MSC, that's the MSC for the ME scatter correction, which I showed you. Here we have a very chemistry specific. So you can say we start with a single reference spectrum and search around this reference spectrum. If you, for example, look at this scatter autoencoder, which was showed by Christian, where we used different reference spectra for correcting spectra, and afterwards train this autoencoder on this. We are staying with this fungi. Then we have been also continuing actually doing. Okay, so then we have a network which is only trained on fungi, and the one which I just showed to you, where we have this pollen, algae, lipids, etc. But we also recently worked with one where we actually opened up more. So we trained with basically peaks, which were like randomly distributed over the infrared spectrum. And again, we sampled from this, and we trained a neural network based on this, which is called PCLIN. In the same way, we do morphological conditioning. You can either use the model for a sphere. You can use something which I didn't talk about. We have high numerical averages. We also need to take this into account in the modeling. We can use nested spheres. We can use nested spheres where we actually put this outside the center. But this one we don't have any analytical model, so it's not so easy to simulate. We use then actually methods from electromagnetics in order to get solutions for such a system. That's actually very highly like in classical dynamics, you can say a highly chaotic system as we talked about in the afternoon. So then, actually, I think I'm approaching the end. I think I will jump over this one and show you this one. So that's very interesting thing. So if you look at these different neural networks, there's something which I could call deep fake spectra. So in examples. So you see, for example, what is this neural network, which is trained on chemistry, so like different data set from fungi, etc. What this does when I, for example, have a spectrum, which is basically only noise, it would make up a spectrum. So that's also something, I mean, we can talk a lot about these things. This is what we call peak-lin, where I don't give any conditioning. So it doesn't expect to find a fungi or algae or something like this. This understands actually what it is. That's noise and CO2. Then on the other hand, if you look at this one, this chem-lin, I mean, it knows about filamentous fungi. It's expected to have a unsaturation, also this unsaturation peak around 3010. So it finds it from this one. But this peak-lin doesn't find it because this interprets it as noise. So then you really go into it and try to understand what a neural network is doing. Also like this figure, sensitivity map, which shows you what actually the neural network uses from so here you see the raw spectrum, and it tells you which parts of the spectrum the network uses for reconstructing the pure absorbance spectrum. And you see, for example, this peak-lin, which doesn't know anything about chemistry, is simply trained on different peaks which are randomly distributed. And so this is actually information more or less all over, but also a lot in the area where you don't have any absorption. The chem-lin, this uses information from one part of the spectrum where there's not so much scattering, and it actually then reconstructs the other parts of the spectrum. Okay, so then I thought in reply to Harald, it's possible to work precisely and be approximately right. So using models from physics and chemistry and employing and using data you saw I wrote this last minute. What I want to say is, and then using data models and model with this around these stable models, this gives a very high degree of stability. And then also something what we discussed today, I wanted to say, I mean, most data sets in infrared spectroscopy, I mean, that's an exception when you can generate and simulate a lot of data. Most data sets, they are not big enough to be able to let the neural network do the whole job. So therefore, it's really important to understand the mechanisms of both chemistry and physics and use them to find a solution. And that's actually the same in the field of infrared microspectroscopy. So we have a lot of our stuff in our GitHub. I also want to mention we use this Quasar and also put models and things into this Quasar, which is a very nice machine learning tool. And we also have our summer school where we use this Quasar as a platform to teach broadly chemometrics and machine learning methods. So some PhD master students or is interested in this will also run this year. And that's our group. Thank you.
I will start with a question. Could you go back like 3 slides? Here, what are we seeing? Is the weights per layer or?
Yes, so it tells you actually which regions of the spectrum the neural networks uses for reconstructing the pure absorbance spectrum.
Yeah, but how do you calculate these values? Like is GradCam is?
I have no idea. I'm not you need to ask Lars.
Probably Christian knows.
I wouldn't guess that.
Yes, yes.
No, it's GradCam
Yes.
stores. Okay. Questions from the others, please?
I think the most obvious question is, this scattering is correct for a sphere, but the cells are mostly not spheres, they are not ellipsoids. And furthermore, they are packed, so you got multiple scattering. So how do your approximation copes with these limitations?
Yes, so I can go to the slide. Actually, you start with the last one. You get very little multiple scattering because so typically when you have a section also in a tissue, or a section of a tissue, and you have cells there, you don't have them on top of each other, so they're actually besides each other. And then so we check this in this article. But actually, yeah, here coupling of the electric particles and signatures in the infrared spectroscopy. So with the numerical apertures we have, it has more or less no effect. So even if they are nicely packed, and that's because the biggest part of the radiation comes from the top, goes through the cells and goes to the detector. I mean, there's very little effect of this coupling or whatever, or there's no multiple scattering.
It's transmission.
That's transition spectroscopy. I mean, the question is correct. We saw the same thing at the beginning. There was even an article which did some really weird theory around this, about this multiple scattering and blah, blah, blah. But you can do calculations. We did this calculation, electromagnetic calculations, numerics with different systems. And we also did measurements, and there's almost no effect from the packing of the cells. Then for this deformation, I mean, it's also a very good question. It turns out that again, I mean, we are only, as I said, approximately right. So it turns out that deformation changes. It moves, these wiggles partially and so on. But what turns out actually, this PCA model, for example, in the NIR MSC of the NIR solution, gives a very nice approximation for this effect. And also what is actually very nice, what we also investigated thoroughly, it's something that Harald also mentioned. So if you, for example, use one absorbance spectrum and you compare it with another pure absorbance spectrum, and you look at a scattered spectrum for this situation, and you use this one in a model in order to correct this, you will never get a perfect fit. So you need to have the same chemistry in order to fit this. So we don't have this. The chemistry makes that you don't have this sloppiness in the system, and you need to actually iteratively move towards the correct chemistry here in order to be able to at the end predict the measured spectrum.
Did you make any goniometric measurement, like measuring the phase function, the scattering phase function? Would it be interesting?
It would be interesting, but I don't know how to do it in this system. So it's the system doesn't measure the phase. I mean, that's correct. I mean, if you could measure the phase, we know even more about the system. We could have probably even better models for inverse models, but the system is not such that we can measure the phase.
Yes, David.
Maybe continuing on the phase, it reminded me of some of my old work, and there is I don't know if you are familiar with the funnel theory, funnel line change, which reminded me of your distortions, which in my world, coming from the coupling of the modes, for example, to some nanoparticles or something, and it kind of mixes the real and imaginary part of the reflective. So would your theory be possible to distinguish those two effects? Because then, like, it would be great for, like, also a more solid state, nanoparticle, nanoscience, which are looking a lot into couplings between molecules and particles, and this could be great for them. So, would you be able to distinguish properly between the scattering and the, for example, the couplings and distortions coming from the funnel line shapes?
Yes and no. I don't know exactly precisely this problem, but it's very similar. I mean, you have this Kramer's chronic relationship between the real part and the imaginary part of the refractive index, and that's what we use in the what we need to do. For example, in this approach, we always need we start with the we sample from the constant part from a certain range, then we estimate the imaginary part as from a reference spectrum. That's our first guess in a way. Then we use the Kramer's chronic somewhere here in order to calculate the fluctuating part, and we use this. That's what we're doing, and here we can actually then at the end figure out this complex thing. But I guess I need to look into we need to discuss probably a bit more what exactly you want to work on. I know it's a little what you're talking about.
I know also a little bit zero, but maybe you have additional customers.
Okay.
Any more questions?
All right, comments on quick question about if you started out with a different for the same empirical data, if you start out with different initialization of your iterative process, would you still end up with the same optimum? You have found a global optimum, you mean?
Yes, not a global. So the thing is that, and that's in a way the drawback of this of the iterative approach, which is only used in this approach for the MSc and not in the last part, which I showed, just to say this. But here you normally need to start out with a good guess of the reference spectrum, because it's, as I said, it's a ill-posed problem, so it has local minima. So you want to be close to this, but you can we also have in the algorithm a mechanism which tells at the end we are far away from the problem. So it could be that you start out with something which is completely different and where you don't. But what we then do typically, I mean, we sample from around or whatever. I mean, there are different tricks in doing it, but you're completely right. I mean, it depends on what you use, and then that's this scatter autoencoder. So there we used. So how we solve this problem, this scatter autoencoder? So let's say you have a lot of different fungi, and then you could we trained a model where we used the correct reference spectrum. We knew, because we knew what we wanted to correct, is the correct reference spectrum. Got a nice correction of a whole image. Okay, then we use a different fungi with the corresponding reference spectrum and corrected it. So like this, we build up a large database of corrected spectra with the scatter spectra, and then we trained this scatter autoencoder, which then afterwards can decide automatically, in a way, what is implicitly the right reference spectrum. But that's a way also to solve the problem.
The reason why I asked is that our experience in this very simplified system with the mass action, low mass action, we found a two-dimensional subspace in the parameter space of equally good parameter combinations. Then when the mathematicians saw this, they could transform this manifold in such a way that this banana became linearized. And what happens then is that there was sloppiness, or the problem of the inverse problem was reduced to one dimension. So instead of saying, no, we can't do it because we have the problem with the inverse problem, instead we found that yes, we could do it except for one dimension. It's a null space that we cannot distinguish. In my opinion, it is along those null spaces that biology has developed, because there the evolution can develop without dying, while the other dimensions are kind of fixed because they have consequences. But along those null spaces, the evolution can happen without consequences.
So you can, I mean, you can show nicely, and that's what I mentioned before. If you look at two different spectra which describe the pure absorbance. So you start with two different spectra, and then you use this one for getting a scattered spectrum, and you use this one to model this scattered spectrum through meteorite. It doesn't work. So you're coming very close, but you have an error at the end, and that's related to the chemistry all over, and that's because actually this pure absorbance will affect the fluctuating real part. So the real part of the refractive index, the fluctuating, and these together actually make so really clear changes that you're not able to fit this. And then the error between these two in the scattered spectrum, so this means actually in the what you are supposed to measure, the difference between the measured and the one you've estimated. If you feed this back and then slowly, gradually go towards the right thing, you will make it. But I mean, you're right. If you start very far away from this, you may not able to end up with the right solution. But that's very often also quite academic thing. I mean, we know that we are working with fungi or whatever, so it's not a problem in our case. So I guess you're tired.
Okay, let's thank the speaker again.